Namaskar, my dear friends. As we are talking about intelligent power module designs, IPM designs, so we have taken an example from SLIMDIP-S package, which is a DIP IPM series. So what we are going to do in this session is we will be designing short circuit protection, and how shunt resistor design is very important. So we will understand how to design the shunt resistor value for your application. So quickly we will understand what is the recommended rating for this particular IC, which is SLIMDIP package, which is S. So as we can see, the VCC supply voltage is typical 300 volt. We have control supply voltage is 15 volt. So generally control supply will be, like high side gate driver, low side gate driver and all. And we have VDV, which is control supply voltage again between these. So which is going to be again 15 volt. We have dead time, which must be more than 1 microsecond, and we have PWM frequency, which must be less than 20 kilohertz. Generally we work with 5 kilohertz or 10 kilohertz. And we have PWM on and PWM off time, which will be more than zero point 0.7 microsecond, that we have to take into account. We have VNC variation that can go up to -5 volt to +5 volt. So this is nothing but the ground potential. And we have the junction temperature, which must not exceed between this range, which is -20 degrees centigrade to 125 degrees centigrade. Now let us talk about short circuit protection, how this IC is functioning for short circuit protections. So as you can see, a very small block diagram is shown here with the driver circuit of our IGBT. Okay. So we have the motor control output here, which we have, like U, V and W, which will get connected to my motor for different phases of motor drives. And then we have the terminal, which is NU, NV, NW. That was my negative terminal of DC input. So this was my positive terminal of DC input, which is 400 volt or 300 volt, let us say. And this is the negative terminal of DC input. So here only the thing is we connect this shunt resistor, and that is what we are going to calculate this particular value, so that we can save or we can protect our driver IC. The thing is, it is also connected to my scene. So scene is nothing but the short circuit protection, which actually helps to shut down the IPM during a short circuit phase. So in that case, we will be utilizing here RC filter, which will smoothen the circuit. So how to calculate the shunt resistor for our design is, we will be having R shunt value, which is going to be equal to my VSC reference divided by short circuit current, that is SC. So generally VSC reference is actually given in the datasheet, which is 0.48 volt, and we have to also make sure for the design of this RC value such that my tau, that is time constant, must be between 1.5 microsecond to 2 microsecond. That is other understanding. However, our main concentration on this particular session is to design the value of shunt resistor using this particular expression. So let's proceed. What we can have is, as you can see, we have short circuit reference voltage. So for different temperature ranges, or like different conditions, we have minimum value, typical value and maximum value. So as you can see, my short circuit reference voltage is varying from 0.455 volt to 0.505 volt. So this is the idea. We will be having our shunt resistor also, which will be having minimum value, typical value and maximum value corresponding to the short circuit reference voltage. So as we can see, to have the minimum value of shunt resistor, we will be dividing it by short circuit maximum reference voltage. That's the understanding. A short circuit maximum current, that's the understanding. Okay. Similar to that, if we want to have R shunt typical value, then we'll take 95% of like minimum value that has been calculated, and if we have to have maximum value of shunt resistor, then we'll take 105% of that. That's the understanding we have to have. So this is what it is saying, plus minus 5% tolerance, my shunt resistor will vary. Okay. And at the same time, we can see we have short circuit typical value, so that will come up as short circuit reference typical divided by R shunt typical, that has been calculated. Similar to that, what will be the short circuit minimum current? So that will be my short circuit reference minimum divided by R shunt maximum value. Okay. So in these cases, we will see that, let us try to understand and find out. If we are going to utilize, like 0.48 volt as short circuit reference voltage, okay. So for, let us say, 20.8 milliohms of resistance, we are going to have how much short circuit current? So short circuit current is coming to be 20.9 amperes to 25.5 amperes. Okay, so this is what the understanding is. And now how does it work out? So when we know the short circuit trip level of this particular IGBT, we can always divide it by V short circuit reference voltage divided by short circuit trip level of the IGBT. So let us say the maximum short circuit was 25 ampere. So you can divide it by 25. Then we will get the minimum value of R shunt. Okay. So hope you have now a good understanding about how to get your minimum value of shunt resistance and maximum value of shunt resistance and the typical value of shunt resistance. So in the design phase, what we can have, we can always go ahead with around, I'll always suggest keep the shunt resistor value in such a manner that my trip level of IGBT short circuit current should be little lesser. So let us say it says 25 ampere of short circuit current, trip level, then we can design it for 20 ampere so that our IC is always safe. And that's a good idea of, designing a circuit. And in that case, we can increase our shunt resistor a little bit. But one more problem that happens, it is seen, is there will be a little bit heating situations that we can always, solve it later on. So if you see in a circuit which was given in the block diagram, what is happening is we have this NU, NV, NW, and we are going to connect one shunt resistor. This is the design that we are doing, and this shunt resistor will get connected to the our ground, which is VNC. So VNC is nothing but the this is control side ground, and this is power side ground. Okay, so this is my GND terminal, and at the same time to the negative terminal of the DC power supply, which is the D point. So this D point is getting connected to my C in point. So C in actually the short circuit protection drive circuit, which is going to switch off our LVIC, that is my low side gate driver, and this is how my IPM will be switched off. So this is the complete functionality of my short circuit protection. Now we'll talk about how the short circuit sequence occurs. So before that, if you talk about short circuit, what happens is if a load circuit occurs, okay, if a load short circuit occurs, like my motor has, phase has shorted or something like that, so excessive amount of current is flowing through the IGBT. So in that case, what happens? The system controller malfunctions, causing a shoot through, that is very high current flows through the IPM. So the IPM built-in short circuit protection will prevent the IGBT from being damaged. That's the best part that is there in the IPM. When a current through IGBT exceeds the short circuit trip level, which is SC, an immediate control shutdown is initiated and the fault output is also triggered. So my fault output, which was already discussed in the previous session in the pin description diagram. So in that, what will happen? It will go low, and low was active, and this is how it will be communicated to the controller, like microcontroller or somewhere, that the IGBT is in fault condition. That's all. Coming back to the short circuit protection sequence, so how it happens and what it happens. Okay, so let us say we have A1, A2, A3, A4 that has been communicated here, but roughly I'll tell you what is happening. We have input signal low on. Okay, so low is on, that is my input signal. Condition of protection circuit is set here, so this condition of protection circuit is high right now. Now gate of IGBT is there, which is going to come here. Now what is happening? My output current through the IGBT is flowing like this, which is my A1. So the normal condition when IGBT is on is A1, right? Now as soon as it reaches here, you can see there is a short circuit, so a shoot through has happened in the current, output current in the gate. So output current in the IGBT has increased suddenly, and in that case what happens? My fault output signal will go low. This is how the communication has gone to the short circuit protection, that fault output signal will be become low by shutting down the low side, a gate driver. And as soon as it becomes low, the IPM will be shut down, and this is how it will be communicated that the IPM is in short circuit mode and we are going to shut down the IGBT. So you can have, you know, like other understanding, like if the points, if you want to see very closely, as I told you, like A1 is the normal operation when IGBT is on. So this was IGBT on, proper understanding is coming up. Then if we have A2, which is short current detection. So as you can see, there is a short current detection because it has gone beyond trip level. This is my SC trip level, that is short circuit trip level. So it has gone beyond that. That's the reason A2 is coming up. A3 is IGBT gets a blocked softly. So IGBT is in A3 mode, which is going to get blocked. So slowly we are going to switch off this particular IGBT. Now F4 actually the point where IGBT turns off gradually. So you can see A4 is the place where IGBT is getting turned off, and my A5 is the term which is going to give you the fault output signal, which is typically taking a time of 1.8 milliseconds. So from here to here, TA timing is 1.8 millisecond total. Now you can see we have A6, which is input high signal, which is off. So A6 is nothing but this. So A6 is high, which is off, and A7 is low, which is on. So you can see A7 is on, because A7 cannot be off because it is taking the input. And we have A8, which will be maintained. So where is A8? This is A8, which will be maintained off, and that's how we are saving the IGBT from short circuit event. Okay. So hope you have a very good understanding about the short circuit protection sequence, how it occurs, and what are the different techniques to design this particular shunt resistors values based on the short circuit trip level, and what was the exact diagram of this particular short circuit protection from the block diagram that we have understood. So if you do have any questions regarding the understanding of short circuit protections and how to design the shunt resistors, we will also study how to design the shunt resistor for each of the three lines, that is NU, NV, NW separately. But this is the overall understanding of designing a short circuit resistor for intelligent power module that we are having for our different applications, which is involving like air conditioners, which is generally involves audio fans or something like that. We have cloth washer or like washing machines, we have refrigerators, dishwashers, fan, pumps. So wherever we see, we will be needing an intelligent power module, like application that will be needed always. So hope you have understood everything. If you do have any queries regarding this or any understanding or any particular questions regarding this, please put down your questions in the comment box and we shall be answering you shortly. Thank you.